Alright, so once you've cut out your foldable, you'll put it on page 4 of your interactive notebook. You'll title this page Domain. If you'll open up the first tab, we're going to look at finding the domain. Please remember, finding the domain is the same thing as looking at those x values. So what x values are being used on the graph. So what x values have points associated with them. So in this first one, there's just a bunch of dots. And so you'll notice there's a total of 6 points. There's one at, for example, -2, -1. There's one at, for example, 1, 0. So when I go to write the domain of this, because they're just single points, I'm just going to simply write the x value of those points as the domain. So I have D to indicate that it's going to be the domain. I'm going to use the set notation first. So I've got my squiggly bracket with my x and then the /, and I'm just going to simply list those x values that are being used. In this case, -5, -2, 0, 1, 4, and 6, and I'm going to close it with a curly bracket. So this is my domain in set notation. Now, because interval notation gives a set of numbers between x's, we don't have any lines connecting any of these dots, so this is not going to have any interval notation associated with it because these are just single points instead of lines between points. So there will be no interval notation. Now, if you happen to have a graph that has a hole, we know those are excluded from the domain. So in this case, we have a hole at 2, -1, so x equals 2 will have to be excluded. But you may also know that this is called a vertical asymptote. Your teacher may have told you what this is. It is simply a vertical line that the graph gets closer and closer to, but it never touches and it never crosses it. As a result, that x value will also be excluded from the domain, but everything else can be used. So that means everything to the left of -3, everything from -3 and between 2, and then everything from 2 and past it. So if I want to write that in set notation, it becomes a little bit lengthy. So I'm going to have my correct curly bracket and x / first. In order to write that x is between -∞ and -3, I'm going to write -∞ is less than x is less than -3. So I'm saying everything to the left of -3 is part of my domain. And I know that because I see these values here with this line connecting them. So all of those x values are part of my domain. When I get to -3 itself, that vertical asymptote has to be taken out, so there's simply a less than symbol instead. And then I pick up between -3 to +2 next. So to show that x is between -3 and 2, I'm going to write -3 is less than x is less than 2. The -3 is not included because of the vertical asymptote, but the 2 is also not included because of the hole. And then finally, for my last set, I'm going to write 2 to infinity. So this is going to start at x equals 2 where the hole is, and everything to the right. So to indicate that, I write that as 2 is less than x is less than infinity. For my interval notation, I'm going to take away all of those curly brackets and my less than and my x's. I'm just going to simply write the numbers in 3 separate parentheses for the 3 separate sections of the graph. Those to the left of -3, so -∞, -3 in parentheses for both of those because I can't attain either number. From -3 to +2, and then from +2 to infinity. This is going to be my domain in interval notation. Now, there will also be some times when you have graphs that have gaps in them. And so there's going to be a whole big section of the graph that's not being used. So in this case, when I go to write my domain, I'm going to only have the domain for the section that is being used. So for example, in this one, from -5 all the way up to +1, that's going to be this section right here, from -5 to +1, all of that has a graph at it. It has a line connecting those points. So therefore, that's going to be part of my domain. So I write that as -5 is less than or equal to x is less than or equal to 1. Because these are closed dots here, they have equal to symbols on those less thans. One more section because of that gap. I'm going to start now at 2 and I'm going to go to 5. Now 2 has a hole at it, so I'm going to put a less than symbol, but 5 has a closed circle, so I'm going to put a less than or equal to. So the second section of graph that has x values or domain, it's going to be from 2 to less than x is less than or equal to 5. And then I'll write that in interval notation. I'm going to write that as -5, comma 1, and you'll notice both of them have brackets. For the second one, I'm going to write 2 comma 5, but you'll notice only the 5 has a bracket and the 2 has a parenthesis. Now, we're going to open up the second tab when we're finding the domain of a polynomial. Polynomial equations are equations that have no negative exponents. They have whole number exponents, which means no fractions in the exponents. They have no variable in the denominator, and they have no variable under a radical. These are going to be examples of polynomials. So, the equations that you have were 2x plus 1, negative b squared minus 2b plus 3, and 2s to the fourth plus 3s cubed minus s. If you look at all four of these stipulations, there are no negative exponents anywhere. They're all whole number exponents. There's no fractions with variables in the denominator, and there's no radicals with variables under the radical. That means if you look at this graph of 2x plus 1, the graph goes on forever to the left and forever to the right. There are no restrictions. Same thing is true for the parabola and this graph as well, which means the domain of a polynomial actually has no restrictions, which means the domain will be negative infinity to infinity. So I've written that both in set and interval notation. Next, fractions. When you take the domain of a fraction, please remember the denominator cannot divide by 0. So you have to exclude, take out any number that makes the bottom 0 with the denominator 0, because we know from our Algebra 1 days that a number over 0 is undefined. So in the example that I've given you, g of t equals t plus 3 over t minus 2. The t minus 2 is the denominator. Whatever number makes that 0 has to be excluded from the domain. So if I look at the bottom and I look to see what number makes that 0, that number is 2. What's going to happen then is I'm going to plug in 2 into the top. 2 plus 3 is 5. 2 minus 2 is 0. I cannot take 5 and divide by 0. Therefore, t cannot be equal to 2 when I'm doing my domain. I have to exclude it. To show that in set notation, I'm going to split this up into two pieces. All the numbers to the left of 2 and all of the numbers to the right of 2. But 2 is not being included, as you can see, using the less than symbols on the 2. Now, the interval notation works the same exact way. I've got negative infinity to 2 are all the numbers on the left, 2 to infinity are all the numbers on the right, and you'll notice I'm using a parentheses instead of a bracket to show that I'm excluding the number 2. Now, what's actually happening when you have the number divided by 0, that 5 divided by 0, is that t equals 2 is actually creating a vertical asymptote on our graph. And you can see that. This is the true graph of g of t. And you can see that there truly is a vertical asymptote at t equals 2. And so, like we talked about in the first part of this, whenever you have a vertical asymptote, that number has to be excluded. And that shows mathematically here by having that 5 divided by 0. And then finally, radicals. You cannot take the square root of a negative number, okay? So if you have a radical, that's the one with the square root symbol. If you have any number that makes that radical negative underneath the radical, then that is going to be undefined. For example, the square root of negative 4 is undefined. So what I'm going to do in the example that I've given you, h of p is equal to square root of p minus 4. I'm going to look at a few numbers to see what numbers make it 0. Negative underneath. For example, if I take p equals 0 and plug it in, I get the square root of 0 minus 4, which is the square root of negative 4. That's not good. I cannot have p equal to 0, therefore I have to exclude p equals 0 because of the square root of a negative 4. If I do the same thing with p equals 1 and p equals 2, all of these give me values that are less than 0. So as a result, none of these values will be able to be used. So I could continue this process, but instead I'm going to take what's under the radical and I'm going to set it greater than or equal to 0. I want the number under the radical, which is called the radicand, to be greater than or equal to 0. So p minus 4, take away the radical. I want to make sure that it's greater than or equal to 0, so that's what I'm going to write. If I just simply add 4 to both sides, I know that p has to be greater than or equal to 4 then. What that means, if I plug numbers in like 4 minus 4 is 0. The square root of 0 is 0. That one is allowed. If I plug in 5 minus 4 is 1. The square root of 1 is 1. That number is allowed. Any number bigger than 4 is going to be part of my domain. So if I want to write that in set notation, this is what it would look like. And if I want to write that in interval notation, this is what it would look like. Notice I have a bracket on the 4 and I have a parenthesis on the infinity. Now, if I wanted to look at what the graph of that actually looks like, this is the graph. If I plug this into my calculator or Desmos, this is what the graph would look like. So if you look at this graph for the square root of p minus 4, you will notice at p equals 4, it hits the x-axis, so it's an x-intercept. It is part of my domain, so that's the p equals 4 part that I'm allowed to keep. And then you'll notice there's nothing to the left. P equals 0 is not allowed, p equals 1, p equals 2. Those are the ones that gave me those negative values. There's this big old huge gap. But if I plug in 5, 6, 7, and so forth, when you plug those numbers in, they do give you positive numbers under the radical. So it's going to create this graph that I can connect the dots for. So my domain then does match my graph just like it does on my equation. And that is it for this page.